Hello everybody, my name is Emad Mehdizadeh. I'm from UT Dallas and I'm here to present a two-stage aerosol impactor for embedded with MEMS balances for particulate size distribution and mass concentration analysis. Why is monitoring airborne particle important? The studies have shown that there is a correlation between life expectancy and the quality of air in urban environments. Also, in mines, the quality of air should be kept at some standard levels. Here you can see the black lung of a 40 years old coal miner which has been overexposed to dust in a coal mine. But on the left you can see the healthy tissues of a young and an old 90 years old man. Also, the quality of air at highly controlled environments like operating rooms and also clean rooms should be kept at some standard levels. Most of currently available particle monitoring systems are optical particle counters. On the right you can see a more advanced system that using a scattered light from particles passing through a laser beam. Particles can be detected. Using such system, we can detect particles down to 100 nanometer in diameter, and using some more advanced techniques, the particle sizes can be grown to some detectable level, and you can maybe monitor particles down to 10 nanometers. However, such systems cannot actually do mass concentration analysis and just do the particle count, and it cannot differentiate particles if it's like 10 nanometer or 100 nanometer. Recently, in the few past decades, microscale mass balances have gained a lot of attention for this purpose. The main challenge in such systems is how to align the streamline, the jet streamline on the microscale resonator or device. Different approaches have been proposed. In here, actually, heated stage was used to drive away particles and have them collected on a F-bar resonator. An 8-piece assembly was used to do the alignment in this system. In another system, an electric field generated between the ceiling case and a microcantilever was used to collect charged particles onto a microcantilever. This system is only capable of actually monitoring charged nanoparticles. In another previous work of our group, we used a partial vacuum to actually direct particles right on top of a resonator. The microscope lens was used to align the jet stream right on top of the resonator. This system was also kind of bulky. On the other hand, there have been these cascade inertial impactors on the market that are capable of monitoring air samples down to a few nanometers. In this system actually consists of several stages, and each stage consists of one or multiple orifices and also an impaction substrate. Particles with larger diameters will be collected on the higher stages, while smaller particles will remain airborne and go to the successive stages and will be collected according to their diameter size. The main bottleneck for such systems is that they are not capable of doing real-time measurements. We recently proposed a system, a very small and custom-made impactor, single-stage impactor, and we embedded thermally actuated resonators for real-time mass concentration monitoring of particles larger than 200 nanometers. In here, we are presenting a two-stage aerosol impactor for not only to mass concentration monitoring, but also to size distribute air samples from different environments. To briefly explain how an inertial impactor works, we have this picture in here. As you can see, particles with larger diameters will tend to stay in a straight line and will be collected on the impaction substrate, while the smaller particles will tend to remain airborne and go to the next stage. The smaller stage, as we talked, can be collected in the successive stages of the impactor. The governing parameter for designing aerosol impactors is the Stokes number, which is a dimensionless parameter, which is the ratio of characteristics response time of particles to that of the fluid. Usually, the particle sizes that are collected with 50% efficiency are called stage cut point, and that's what we use for showing what the stage cut point for each stage is. Another important parameter is the Reynolds number, which is another dimensionless parameter, which states the ratio of inertial to viscous forces. To design inertial impactors, we use a collection efficiency curve, and this collection efficiency curve shows that Reynolds number between 500 to 3000 will give us the sharpest efficiency curve, which is best for designing the particle sizes. Having the right Reynolds number, we can find out what is the best Stokes number, and using the Stokes number, going back to this formula, we can design the number and also the diameter of each nozzle for each stage. These are the parameters we've come up in this work. We designed actually this impactor parts and machined them out of aluminum. This is the first stage with 2 nozzles, each 250 microns. The second stage has 6 nozzles, each with 100 micrometer diameter. These are the alignment pins that we will later on use to align the MEMS chips with the nozzles. And here you can see the exploded and also the assembly view of our whole system in SolidWorks. These are the PCBs that will carry our MEMS chips. To assemble the systems, these precisely diced MEMS chips will be placed on a specifically designed PCB. We have 2 of these for each PCB for each stage, and then each of these PCBs will be assembled with the correlated impactor stage, and at the end they will be tightened using bolts. And here is the micropump we will use for making the partial vacuum on the on one side of particle counters. How to align the sample to the microscale resonators with the orifices. As I said, we have these precisely diced MEMS chip. By pushing the edges of these chips against these 3 pins, the microscale resonators can be exactly aligned underneath orifices of each stage. We are using a thin film piezoelectric on silicon resonator, and this work upon application of an electric field between the 2 metal layers. These resonators can be actuated in the lateral extensional mode, and the charged particles generated from the resulting stress and strain as a result of the piezoelectric effect will be harvested from the output. And here you can see the fabrication process was used for fabricating these devices. Here is the schematic of the experimental setup. The resonance frequency of each of the resonators in each stage were monitored continuously in real time using two separate network analyzers for monitoring air samples from three different sources: regular laboratory, air purifier, and also clean room air. Here you can see the optical images taken from the two resonators in each stage. Here is the resonator for stage 1, and this is for stage 2. You can see how the alignment process presented system works out in aligning the jet streams right on top of the devices. Here the SEM pictures show that larger particles are collected on the first stage, while the smaller particles down to 60 nanometers are collected in the second stage. Obviously, by adding the number of stages, particles smaller than 60 nanometers can be easily collected for like a similar system. Here are the measurement results. The measurement results show that air purifier is almost as effective as the clean room filter in filtering large size particles. However, the air purifier is not as effective for collecting and filtering smaller particles, because the mass concentration of the air sample for actually the second stage is not as small as expected. The graph on top is the result from the stage 2, and the result on the bottom is from stage 1. Also, the number of particles per cubic meter in UT Dallas clean room was estimated using the obtained results to be 9 multiplied by 10 to the power of 4, which is comparable to the value of 4 multiplied by 10 to the power of 4 obtained from a particle counter. To conclude, we proposed a two-stage aerosol impactor with embedded MEMS resonators. The results show that the results were validated with an optical counter, and it shows that this system is well capable of high precision real-time size distribution analysis of airborne samples in even a highly controlled environment. At the end, I would like to thank you for your attention, and I'm ready to answer your questions.